In the previous section, we discussed exponential functions. For example, the natural exponential function, which is of the form y equals a times e raised to the k times t. Many quantities in the real world are governed by this equation, at least in the short term. In this equation, t stands for time, and y is our amount or quantity at time t. A and k are constants, and let's see if we can figure out what these mean. At time t equals 0, this should give us the initial amount of whatever quantity it is that we are modeling with this equation. So let's go ahead and plug t equals 0 into that equation that governs exponential growth and decay. Y equals a times e raised to the k times 0. Now anything times 0 is 0, so we have a times e to the 0. E to the 0 is 1, and 1 times a is a. So a is our initial amount, because it's the amount y that we have at time 0 when we start. K is the growth or decay constant. When k is greater than 0, we have growth. When k is less than 0, we have decay. Exponential growth functions, the quantity grows larger and larger over time. With exponential decay functions, the quantity grows smaller and smaller over time. Notice that with exponential decay functions, the quantity never actually reaches 0. 0 is a horizontal asymptote for the function. Let's look at an example of exponential growth. Let's suppose that when a flu outbreak occurs, that the number of people infected grows exponentially. And let's suppose that at time t equals 0, that the number of people who have the flu is 10. And then at time t equals 2 days, that the number of people infected with the flu is 110. Then what we want to do is we first want to build an exponential model which will model this flu outbreak, and then we'll go ahead and see how we can use this to predict a few things. For example, how many people will have the flu in 5 days? Or how long will it be until 10,000 people have the flu? So recall that our model looks like this: y equals a times e raised to the k times t. And remember that a is our initial amount, so I know right now that a equals 10 because we started with 10 cases. If I didn't remember that, I could actually plug in t equals 0. I have y, which in this case equals 10 at time t equals 0. So I have 10 equals a times e to the 0, so I have 10 equals a times 1, so I have 10 is equal to a. So I know that a equals 10. So my model looks something like this: y equals 10 e to the k times t. Now what I'm going to do is I'm going to take the other information, this piece. I'm going to go ahead and plug it into this model, and that tells me that y is 110 when t equals 2. So now I need to solve for k. This is why we needed to be able to solve exponential equations in the previous video. So first thing I can do is divide both sides by 10. Now I need to isolate the k, so I'm going to take the natural log of both sides of the equation to get it out of the exponent. Inverse property of logarithms: natural log is base e, so the right-hand side of the equation simplifies to 2k. And finally, I can divide both sides by 2, and I've got k. So k equals the natural log of 11 over 2. Now if I plug this into my calculator, I see that k is about 1.1989. Now I don't want to use that rounded value. I'm going to keep the natural log of 11 over 2 so that I don't have any rounding error, but I just evaluated k to see that in fact k is positive, so this is a growth equation. And I would expect that it's a growth equation because as time went on, I went from 10 to 110 cases. So now that I know A and I know K, I can write down the model, which will model this outbreak. Y equals 10 times E raised to the natural log of 11 over 2 times T. So this is my model. And I can use this model to make predictions about what will occur in this flu outbreak. Let's look at two examples of using this model to figure out what will occur in a flu outbreak. So here's our model, y equals 10e to the natural log of 11 over 2 times t. And let's begin by asking the question, how many infected people will there be in 10 days? So to answer this question, I'm going to go ahead and take 10 days and plug that into my model. Now t is time and it's in days, so I'm asking the question, what's the value of y when t equals 10? Well, y equals 10e to the natural log of 11 over 2 times 10. And if I plug that into my calculator, I get 1,610,510 people. Another question we could have asked is, when were 500,000 people infected? In this question, y equals 500,000, and we want to solve for t. The first step is to isolate the exponential equation, so we'll divide both sides of the equation by 10. Next, we want to get the variable out of the exponent. We can use the same technique we used when we solved for k. We'll take the natural log of both sides of the equation. When you take the natural log of e raised to some power, it simplifies to the power. That's the inverse property of exponentials. And then next we can divide both sides by the natural log of 11 over 2. When you divide by a fraction, remember you can flip and multiply because division is simply multiplication by the reciprocal. Or multiplication by the multiplicative inverse. And if we work this out on our calculators, we find that t is approximately equal to 9. So after 9 days, 500,000 people have been infected. In general, exponential growth models are only valid for a small set of t. For example, if we plugged in t equals 100, we'd get that y is approximately equal to 1.17 times 10 to the 53. Now that's more people than there are in the world, so it's not possible that we have that many infected people after 100 days. So it's important to pay attention to this fact, that an exponential growth model in practice is not valid for all t. Exponential decay uses the same model as exponential growth. Y equals a times e raised to the k times t. The only difference between exponential growth and exponential decay is that with exponential decay, you have less over time instead of more. For example, suppose we give our information in terms of data points, time, comma, amount, and suppose that we have a substance that at time 0 we have 100 grams of the substance, and at time t equals 5 minutes we only have 50 grams of the substance. Then we can use the same technique to find a and k as we did with exponential growth, and we can write down the model for this substance. The model in this case, and you might want to pause the video and work this out for yourself, would be y equals 100 times e raised to the natural log of 1/2 over 5 times t. We could then use this model to make the same kinds of predictions that we made with the growth model. Given a time, we could be asked how much of the material is left at that time, or given a target amount, we could be asked at what time is that target amount reached. Generally, when we're talking about things that decay exponentially, like radioactive material, what we know is the initial amount and something called the half-life of the material. In your textbook, there's a table of half-lives. For example, iodine-131 has a half-life of approximately 8.04 days. What this means is that every 8.04 days, we will have half as much of the material as we had when we started. So suppose I was told that I had initially 100 grams of iodine-131, and then I was asked to build an exponential decay model. Now see, in the previous example, we had 2 data points. In this example, this tells us that at time 0, we have 100 grams. What we then use is the half-life. The half-life tells us that in 8.04 days, we are going to have half of what we started with. So in this example, we'll have 50 grams. So now that we have our 2 data points, we can build the model just like we did in the previous example and answer any questions. Just to see again how half-lives work, in another half-life, so another 8.04 days, so we're at 16.08 days, I'll have half of what I had previously, which is now 25 grams. Carbon dating is an interesting application of radioactive decay. Organic matter has carbon-14 in it. Carbon-14 is a radioactive substance that decays over time. From our table of half-lives, we can see that the half-life of carbon-14 is 5,730 years. Suppose that we measure the amount of carbon-14 in an item, and we find that it has 70% of the expected amount of carbon-14 in it. We'd like to be able to see if we can figure out how old the item is. First, we need to build a model for carbon-14. Now we know that the item has 70% of the expected amount of carbon-14, but we don't actually have an initial amount. But what we do know is this. It started with some amount A, so these data points are in time and amount. And then, after 5,730 years, it should have half of what it started with. So from that information, we can build a model. The amount, after 5,730 years, is half of what it started with. And then we can solve for K to find the decay constant for carbon-14. First step is to divide both sides by A. The next step is to take the natural log of both sides of the equation because we need to isolate the K. Finally, we'll divide both sides by 5,730. And this gives us the decay constant for carbon-14. So a model for carbon-14 using this decay constant would be y equals a times e raised to the natural log of 1/2 divided by 5,730 times t. Now let's see if we can figure out how old the item is if it had 70% of the expected amount of carbon-14. So the amount y that it has right now is 0.70 times A, 70% of what it should have had. So we'll use that information and solve for t. First step is to divide both sides of the equation by A. Next step is to take the natural log of both sides of the equation to get the variable out of the exponent. Take the natural log of e raised to some power. It simplifies to the power. That's the inverse property, since the natural log is a log base e. And the final step is to divide both sides of the equation by natural log of 1/2 divided by 5,730. Division is really multiplication by the multiplicative inverse, or reciprocal, so you flip and multiply. And if you work this out on your calculator, you'll find that t is approximately equal to 2,948.50 years old.